RP here is Puan Norzalina. And then we are a student who take M8491 Calculus 3. So the RP here is Dr. Rini. Right? And then with I'm sorry. Okay, so with us also Dr. Hakim. So Dr. Hakim also teach M8455. So we invite all the students to join this talk, right, Dr. Vincent? Okay,
Yes.
so my name is Dr. Amirah. Okay, so I'm the leader for this project. So far, it's very great to have you to give a talk to our student. Okay, so here we let's start with some introduction about Dr. Vincent. Okay, sorry, my voice not really good here. Okay, because I have lecture earlier, right? Okay, so Dr. Vincent, this is our speaker for today. The name is Dr. Vincent, so you can call it Vincent. It's much more simpler, but Dr. Vincent, eh? Okay,
Yeah.
so he's currently a staff researcher and also a team leader at Huawei Technologies Canada. So currently he's at Canada right now. All right. So based on, I know that he works on the AI accelerate real-time rendering system, if I'm not mistaken. Can you confirm, Dr. Mason?
Yes. Yeah.
Okay. All right. Okay. And then before this, Dr. Mason take a degree at UTM in mathematics and also masters at UTM also, mathematics engineering, right? Engineering mathematics. And
Yes.
then he doing PhD in Canada, right? Okay, and then currently now as a staff researcher and also the team leader at Huawei Technologies Canada. Okay, so I think that we can start our lecture, our program now. So maybe Dr. Vincent can start now.
Okay.
Who is
All
yours?
right.
Thank
Sure.
you.
All right. Thank you. Thank you for the good introduction. So, okay, let me share my screen first. I just want to make sure that I can, doing all the things right. So share the window, share screen. Okay. Okay. Share entire screen. Okay. Can you see my slide deck? Anybody see my slide deck?
Yes,
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 we
we
can.
Okay, good. So I also don't want, because I think this is just purely about the the graphics applications with the mathematics. I don't want to make this presentation like too long and also too like a lecture oriented, but I just want to draw some of the the interest for everyone online, to know like, okay, so the graphics, the thing that we see around, actually they are related to the mathematics, and in particularly calculus. So calculus is a small portion, if you know that. So because calculus, you have the differentiation and also integration and all sort of that. And I think if you go even further, I think you have explored even more than that. So I think this is just a small topic just to inspire people online, to rethink about the things that you learn during your day-to-day class with your professor in the class, how this, changed, your perspective in the graphics, of course. And I wouldn't make this presentation very long, but I would love to have more like, Q&A chat, if you have more question on it. But if it's somebody like interested on the the question about the the astronaut shirt behind it, so those actually are the rendering from the nanomaterial, and actually that actually was my one of my PhD research. So we'll be able to using the what do you call it, electrodynamics simulation to capture that effects, and then we translate that one into the graphics rendering. So I believe that Mira has a very good make very good introduction again. So I'm a leader, currently as a leader in the cloud media team. So we're working on a very cutting edge research, especially for the real time rendering. So real time rendering with the AI accelerated. So how to make the image, the graphics looks as real as possible. basically we just want to fake it like real life. So that's where we are working now. And also we're working on different kind of the interesting system. So that's what we our currently research is. And also again, I have my PhD from UBCO Okanagan in electrical engineering. So, but my origin was from the bachelor in mathematics in UTM. So I think that was the time that I was not willing to go for study in the mathematics, but once I joined, start to join a UTM for the first year, I'm starting to learn, oh, that's mathematics. And then I switched to, the engineering mathematics during my master degree. But I start to see that, so mathematics actually just a foundation of everything that you can move from one area to another. So then that's we I jumped to like electrical engineering, so specialized in electromagnetic, so which use lots of vector calculus. So that's a very very difficult area that we're trying to tackle the problem, especially in the metamaterial. Um, so actually, I prepared this slide in a very very a short time period. I just also want to share some of the very very nice trip that I went last week for the CES. If you don't know what is CES, is a consumer electronics. It's one of the largest trade show in the world. So especially this is what we see from the from the one of the keynote from the Lenovo in the Sphere, and whatever you see on this one, the rendering. So actually, this is a giant big screen. So they render all the image, in real time. But to make this one happen, so it's not that from 1 to 0, sorry, 0 to 1, that simple. So everything has to be done real time, just like this one. If you can see this, the tree, they're moving in the same time. They also need to streaming the videos, all has to come together, and you cannot have any delay. A slight delay is not acceptable for this kind of the things. But again, that's about the beauty about the graphics, the technology, the compute power that we have this day. So that's a beautiful about the pinnacle of the rendering right now that we able to see in the live scale. And also, and this is what tells us how big the venue is, and also how big the resolution of that sphere inside of Vegas that has to render. So if you see that blue circle, so that is a 8K resolution. So this entire sphere actually is rendered by 18K. So the amount of the sheer compute power, they are huge. But thanks for the all the innovation, also the graphics rendering, and some of the acceleration they do it for making this one happen possible. So, but why I'm talking this to you guys? But actually, I want to bring up to something like the rendering, and this is even interesting that if you have some escape room or some of the life scale experience. So whatever you see on this video actually is rendered in in real time, and those butterfly actually interact with the user when they scan the QR code. So you cannot fake it, you cannot pre-render it, but this thing they render so smoothly. But what are the things behind it? We want to scale for the the detail. So what is the thing drive to this kind of beautiful graphics rendering out there? So bear in mind before that, so let's talk about a little bit about the history of the rendering. So whatever you see from the left side, actually this is the early stage of the the rendering. So sorry about the corneal box. So from the very very basic, the left one is like the backlightings. So they only have not like completely lit up this one, but with all the improvement like the global illumination. So global illumination is like the diffuse light, so it means like they have the multi bounce lights to add up the brightness. And with all the improvement now, we can have, usable computer graphics, computer generated image for this day. And the computational can start from, can use like 6 hours or even 1 days to do this kind of the rendering. But I think this is also one of the very what do you call, like, the latest movie, they're using lots of CGI rendering. But if you don't know what's behind this, the cost to render this one, so usually it would take like at least like 10 hours or even more for a single frame. But imagine like this is a movie with 3 hours. 3 hours means like you have like 180, sorry, 60 times 3, 180 minutes, and then you times second, and then you time 24 frame. So that is the amount of the frame that you need to render for a movie. So to achieve this kind of computational cost, if you say like the one image need like 10 hours. So how long we gonna finish for this movie? So I think that will be take years to finish it. But thanks for all the advanced render farm. So they're using all lots of GPU cluster and also CPU cluster to make this one possible. And also they are doing multiple iteration throughout the production. So this is one of the the graphics that we see from this day. But today, sorry, I just want to share some of the the detail about the technology behind this kind of the stunning, beautiful graphics, computer generated graphics behind it. So this is also the same thing. So you see the Will Smith in real life. Sorry, just need one sec. So for this one, you can also see that this is also powerful CGI. So previously, it's not even happening to see both like Will Smith at different age in the same time, and also they are managed to get the detail rights, because the younger Will Smith, they have the different type of the skin. You see that? So that's how the the graphics, they're doing all kind of the rendering that make this thing happen. And everything they're doing it actually is a physical based rendering approach. So it means they are more stick to the physics of the lights, or the material, surface material that render this effect. Yeah, and this is also one some of the my previous work during my PhD study for some of the commercial work. So this is also using some of the offline render to create this kind of beautiful, stunning image. But you probably will see lots of this kind of image in the social media. So they're using a simple the AI generated image. But and also at the same time they will ask like, so the AI generated image can completely replace the CGI? So that's actually a very interesting question. So I think that will be keep it until the end of the discussion. So I think that will be very, very interesting to explain that. So I think first of thing we just need to know like what is the rendering. So basically the rendering, that what we say here actually is that we're generating the image from a 3D models. So with a computer program. So to generate this one of the image, so we have to use some of the techniques or the mathematical models, so to simulate the lights interacts from the surface to the light. So it's just using our eye to trace where the rays can come to reach to the lights. So there's a multiple techniques they're using for the rendering. So the most the most and the fast way to render it actually is called the rasterization. So the rasterization, if everyone has played some of the the Mario game in the past, just like the 80s or 90s, the video game graphics image that renders on a on a TV, on your computer, those are the rasterization. And the ray tracing is not possible at that time until So until they have the hardware support for the ray tracing, so which can create um, a very like detail of the reflection, and also some of the shadow that looks very nice. And that's actually starting from when the timeline NVIDIA launching the new RTX 2080, the 2000 series GPU, which support the hardware ray tracing. They make the whole thing happen, and the game looks even better than the 90s or early 2000s game. And this is an image. I just want to show you the difference, from the rasterization to ray trace and to the path trace. But you can see the qualities that are different because you can see the shadows. Obviously, path trace is a holy grail, or we say that it's a ground truth that actually supposed to be looks like in real life, because the path trace that we solve, we try to simulate the whole light bounce in the space until that the lights reach to our camera, or our eye to see it. So that's how actually what the rendering is working with. But for ray trace, actually, they're more like simplified version. So it means they just only take like single bounce from the surface to the lights. So that create this kind of it looks real better than rasterization, because rasterization is more like it's developed on the time when the hardware is not really powerful. So they're using the rasterization to you know to fake this kind of the some of the lighting effects, or some of the shadow, and some of the reflection, but they are not really accurate. So that's the difference of the rendering quality. Obviously, if you can compare the computational costs, so the path trace is a very expensive compared to the rasterization. Sorry. So the rasterization is obviously is real time, and path trace previously is only happen in offline, so means it's not real time. But now the path trace can be run in real time. I will talk even more later regarding to this one. This is another image. Just want to highlight key difference between the path trace and the ray trace here. Before we talk about more about the maths behind the calculus behind how do we calculate this kind of the lights behind it, but I can see that so the reflection is there. But one side on the right side of the image actually they are more like the diffuse image is very beautiful, and also they can see some of the light blending, like some of the green lights. So some of the green light they're blending with the shadow, so that gives the very realistic. This is actually how the real light of the shadow has to look like, because the lights bounce under the surface. So that's why they have some of this image here. Sorry, this shadows here. Yeah. So let's just talk about a very simple idea. What is the ray tracing first? I think ray tracing is a very buzzword. I think uh, you know um, like you can hear it from every single social media channel if you are a gamer. So like, oh, ray tracing. So ray tracing. So what exactly is the ray tracing as? So ray tracing so means it's like you're tracing the lights from a light source. So which is like the sunlight here. The sunlight, the sunlight reach to the surface, and then from the surface they bounce continue until they reach to your eye. So that's how you trace the ray. But again, in real life, we are not only trace a single ray, but we're tracing like not just million, or I would say billions of the ray in an image. And so if you consider like 1080, or sorry, 1080 means like is 1920 times 1080. So that's a full HD resolution. So it means like you if you multiply that's like closing like a million pixel. Each pixel that say you have 10 sample per pixel means that you have 10 rays. So if you multiply that, so you can see that amount of the calculation has to done in real time. So that's very expensive and very challenging for those the hardware and also the GPU to do this kind of calculation works. But there's things that we can improve it through the algorithm or through the optimization. So this is how the things that get involved here. So let's go back to the basic. All the magic that you saw previously, those are the nice images. Actually, they are governed by the rendering equation. So this is a mathematical foundation of all the rendering, or we call it global illumination algorithm. So if you look at this one, so looks very simple. So LO means like outgoing light is equals to if the surface is immersive, we have to add the surface of the the lights on top of that. But in the same time, we also need to integrate the surface. So for omega square, so actually this is the triple integral. So we just simplify in this kind of the mathematic notation here. So in fact, this is the triple integral. And then so we have the FR. FR actually is our BRTF, or we call it like the bidirectional reflectance distribution function. So this function actually describes how the surface behave. So with the lights interact to the shine to the surface from what angle perspective and how the lights will scatter, and then with the incoming lights. So that's why we have the Li at a point P. So that's why we define like the point P here. So don't worry, I will have the figure later on to illustrate that. And also, I just want to have the mouse. It's fine. I use the mouse cursor here. It's easy to point out. So again, so the point P. So this is the omega O. So this is omega O means that it's outgoing direction, and so omega I actually is the incoming direction. So the integrate with the cosine theta over omega I here. So this is a very complex mathematical equation, but don't worry about that. So we're not having any quiz later on. So hopefully. So, but so the key example here actually is that they're shooting, the ray tracing. Actually, they are shooting, the ray from the eye. So they reflects, for some of the. This is just want to showcase, the different of the. We want to move into the path tracing algorithm. Sorry. So I just want to make some distinction between the ray tracing and the path tracing over here. And also so the ray tracing actually is very simple assumption. We only trace like a perfect specular reflection on the refraction for that kind of the the image quality. So we don't really solving the rendering equation entirely. But I think the key part of this presentation, actually, I want to more emphasize on the path tracing that solve the rendering equation completely. So means like we take care everything about the lights. We simulate the lights bounce in the room, including the direct lighting and also indirect lighting. So if you don't know what is a global illumination, so basically we are referring to the diffuse lighting or indirect lighting. So that actually makes the rendering effects that looks more real than the regular ray tracing image or some of the ray tracing game that you play in the past. For those having the like playing the games and when you have the free time. So again, that's actually the different. And so of course, with that kind of the the solving the equation completely, so actually you have very very good in terms of the shadows, because you no longer have the very hard shadow, but of course because then you can have the soft shadow in between that makes the things looks more real and stunning, like like the real life. But again, this is very very expensive until they have the real time path tracing algorithm is invented in 2021. Yeah. So, but again, solving this kind of rendering equation is too complicated. It's too complex. So the way we solve it, so again, we rely on the Monte Carlo integration. So don't worry about that. So what is the Monte Carlo integration? So basically, it's something we're using the randomness of the rays. So like just like a Monte Carlo theory, to 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 solve this equation. But again, we're doing some of the integral by taking the random sample, but again we divide them later on by 1 over the number of sample that we have here. So this is actually the equation we are using the sampling techniques for the Monte Carlo integration. So context here, because if you want to calculate the light direction from every single direction, that will be very 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 expensive. But why not? So we can have the random sample light direction from a single point, and that actually help us to to increase the conversion. But again, um, sometimes some of the sample actually is good sample, and some of the not is good sample that it can result like a noise, like the black dots, because again the not good sample that can result the not good accurate of the luminance of the lights. So this is just an example. Let's say just want to make sure, just to give you some illustration what's the Monte Carlo integration over here. So let's say you have the curve here. So this is just like 1D, a regular 2D, okay, 2D images here. So let's say we want to integrate, to find the area below the curve. But if you know the function, it's easy. We can just do the regular integration. But what if we don't know the equation? Same thing, like the rendering equation. So the rendering equation, we don't know about the function here, the surface function or something like functional this function for that one. So what we can do here, so we can select a point like the X here. So we're trying to calculate the, what do you call it? What do you call like the surface? Sorry, the area below the curve. So maybe we'll say like, hey, yeah, some part of the area is covered, but some part of the area is like not really covered. So what happened? But what if we can divide even more sample with different point, and then we add up all together at the end, divide by the number of the sample, like the X point that we have here, we will get equal to the the area below the curve. That's actually just a simple explanation of about the Monte Carlo integration that works in the in the graphics. If you really want to decide to study like computer graphics later, I think you will see lots of this kind of the integration on this one. Yeah. So, and one of the key part of this of the rendering equation actually is most important. Actually, is a BRDF. So BRDF. So in a very simple word to say, actually, is the material properties. So if you see the what do you call it, the bottom left image here. So this is actually the surface would tell how the lights will reflect with the incident lights from the incident beams here. So if let's say the lights is hit on the one's angle, how the the light will spread out. So that's why it, you know if the material is like very smooth, like the mirror, so they will go through like what they call like we call it like mirror reflection. So the whole light will reflect, obey the optical angle. So it means that the if let's say that the surface actually is a glass, so they will use the Snell law. So they undergo some of the reflection. Sorry. So if the surface actually is some rough surface, and that's why you can see that very interesting images that I showcase on the bottom here. So if let's say if you have the rough surface, so they will start to spread the lights a bit. So then you start to have more like the some of the diffuse lighting that you see on some of the surface. And this is one of the example that we do some study about the surface properties. And so the image that you see from this one actually is not from the real photos, and those images actually is rendered by the rendering. And so, but you can see this kind of the glass, because the glass is reflecting how much how rough the surface is. Obviously, the smooth surface will give you a very glossy finishing, but once the surface is getting very very rough, they start to the reflection start to get disappear, and until one stage, so the the images, the shadow behind, sorry, the object behind it, behind the glass will start to disappear. So that's actually one of the the surface model that using the microfacet theory for this result. Yeah. For this one, I don't want to cover too much because this is very complicated. So I just want to make sure that um, this is also very very interesting, that because people were saying like when you're doing the sampling for the rendering, so we talk about the important sampling, just like the Monte Carlo, because Monte Carlo actually is about you're trying to pick the which direction or which sample is the best sample will give you the best result. But again, there's a bias and also unbiased sampling approach, that also would result the calculation a bit diverge from the calculation itself. So because if you see from this diagram here, so if we look at on the eye here, so actually the rays here you can sample from more than one direction. But again, you also want to make sure you sample the light that hits the next surface that also can hit the next surface like that, because this is also like another probability that we need to consider that, because this is a way that we're trying to path trace the rays until they finally reach to the light source, and then we can start to pass the value from the light source, to our pixel calculation for the final image generation. Yeah. And then so for the problem on the rendering, because most of the problem that we have before that, actually we have a lot of noise because of some of the sampling doesn't give us very very good result, so they're causing a lot of white noise. So that's come up with lots of problem that we can either increase the light sample, but again, increasing the light sample can be very very computation expensive, because now if let's say if you have um, if you know the current GPU, let's say if you have 4090, so for real-time path tracing, the maximum sample per pixel budget actually is six sample per pixel, that maximum allowance that you can run on 60 frames. So again, if you want to go beyond than that, so that will be very very expensive. So the way they're trying to to achieve that kind of the noiseless images, so they heavily rely on the denoising techniques. just like the NVIDIA optics, and also sorry, or the DRSS, some of the denoising technology to remove the all the noise, from the rendering. It looks very, very nice. But again, the starting on the denoising technology actually are not really, really perfect yet. But again, this is how this is the way of the graphics people's thinking. If we can fake it, just fake it until make it. So this is how the graphics in this day, because we know if you rely on the pure computing, actually is very, very expensive, and you won't able to achieve this kind of the rendering quality. Because if you want to use that 4096 sample per pixel, that probably would take you around like 20 minutes to render one image like that with this kind of hardware. 64, maybe that will be done in 10 seconds. But if you have the denoiser, that can run like in just a split second. They get a very beautiful image because they can use the AI or something to estimate the pixel values, and that's create a very, very beautiful image. And that's also how the modern graphics game they are using right now. So like the Cyberpunk or the Minecraft, you play that. So so the image actually getting better. Sorry. And this is one of the image actually I took from from the website. So if you can see this one, actually, this is actually the real-time path tracing by Cyberpunk. But you can see that all this kind of the image done by all the denoising. Of course, they have some like path tracing and also the global illumination. It makes the image looks very, very realistic. You know, compared to if you don't turn on that kind of the rendering effect or just rely on pure rasterization rendering techniques. Yeah, and this is even more interesting example. This is path trace by very, very traditional methods, one sample per pixel, and this is the image that you will get it. But what happens if have the AI with the neural radiance caching? And this is the way we start to segue to the AI and create this kind of the pipeline here. So once again, so this is a normal traditional path trace without any AI, but with the neural radiance caching. And this is the AI they start to help us to to predict the GI, global illumination, and also some of the shadows. But it still looks good, but it's still very rough or far away. And what if we apply the denoising and the super sampling? But for those that don't know what is super sampling, so means like usually the rendering in your GPU. So usually they will render at a lower resolution, and then you will use the AI to do the upsampling or some of the techniques, or some other techniques like FSR, also using the different special algorithm to upsampling to 8K or 4K resolution. Because if you want to render this image in a full resolution, that will impossible to achieve the real time result like this. So usually they will do it like 1/4 of the pixel, and then they upsampling, let's say from like 720, they can upsampling to 4K or even 8K possible. Yes. Yeah. And then so I think also want to highlight this because when I tried to prepare the slide, so I was trying to highlight something called like people will start to talk about like real-time path tracing. So real-time path tracing is possible now. Sorry, because of the hardware acceleration of the advancement of the the latest GPU that you know launched by NVIDIA or AMD or other manufacturers. So that actually make the real-time path tracing possible. It's not, and also some of the cutting edge the algorithm for the real-time path tracing make it possible. Just one example is a RESTER. It's a spatial temporal resampling techniques. They make all the sampling calculations very, very fast. But again, I just want to give you some idea thoughts here. So if you want to run like 1080 60 frame, so it means like in 1/60 second, you have to finish everything. So that's actually your compute time, or even less, because you need to calculate some of the delay. So again, the computational has to done very, very fast. So that way, how much the streamline calculation that has to be done in a single GPU and then display in the user, and then render the second frame and render the next frame. So that's how the rendering graphics these days working with. Yeah. And then I've started to give some introduction, like from this kind of graphics techniques that you learn in the basic, and we start to talk about moving towards to the neural renderings. And this is actually the starting point of the new era of the graphics, AI accelerated. But again, if you want to purely, path trace or using a very, very high quality image, to render this kind of the movie qualities, or like just like what you see in the theater or the movie theaters, so that would be possible in real time. But because of the neural rendering, so we're able to learn all this kind of the information in a very, very small networks, and then we can run it in the real time. And with that kind of techniques, so we can have the effects that not able to achieve before that. I think so. One of the big things is one of the big breakthrough actually is like they're using the NLP. It's a multi-layer perceptron networks to learn like very, very high resolution texture image into the small network, and then in that network actually can capture very, very small detail of the surface, and then they render in real time. Yes, and also they also using some of the neural rendering, neural radiance caching. So they're using for this kind of what they call like the prediction of the GI, because the GI is the most expensive, most difficult problem to solve these days still. But we're using the AI, to do this kind of the acceleration. And of course, they also have some like material, neural material. So it means that we're trying to represent a surface of the material in a very smaller neural networks, and also we can represent them with more like realistic details. Because in the traditional graphics, we only can put like 2K or 1K texture. If you want to render like 4K in real time, that is very, very difficult. But I know this day, if you're playing some of the AAA title, so those like game texture, they are very, very big. But again, they only can run this kind of the very, very high quality on certain GPU types only, because of the numbers of VRAM requirement or system resources requirement. But with the neural rendering or neural texture compression or any neural AI integration, that will try to solve the problem. That will solve the problem, not only for those high-end GPUs are users only, but they also can run it into like a lower tier graphics possible. And that's actually what we want to achieve for in the future for the gaming itself here. Yes. So I also not making too long or too much light. So I just want to make a very quick conclusion here. So mathematics actually just a key to open a new opportunity. So this is actually based on what I felt like in the past life, not past life, I would say, my past experience. So again, not just like on the one like computer graphics, but it's also fundamental of the world build ups actually. So because again, from mathematics, so it can go to different areas, like very, very diverse, into engineering, finance, or even more. So just think about this kind of the the 1 hours or 2 hours session. Maybe I can bring you I guys more ideas regarding to this kind of uh the application for the mathematics in the real world. Yes. And with this, I'll say thank you. And also, I love to open the Q&A discussion with everyone. Yeah.
Okay. Okay, so thank you so much, Dr. Vincent. I can see that you're not really
Oh yeah.
good condition, but no worries. Okay, because okay, so as Dr. Vincent said that we are open for questions. You can free to ask any question, right, Vincent? Yeah,
Yes. Yes.
not
Yes.
not
Yeah.
regarding the topic actually. So maybe you can
Yeah.
want to ask any of the skill that need in these technologies. Maybe you are
Yes.
interesting, right? Okay,
Yeah.
and then also any career path, any advice also you can ask.
Yeah.
Okay,
Absolutely.
just I have one question. This is my question actually, Vincent. Actually,
Okay.
because we can see that's a lot of beautiful graphic there.
Yes.
Uh, because is that a real or you create it?
So most of the images that I included in the group actually was render. It's not real.
It's not real, and
Yes.
surprisingly, it look real.
Well, that's a beautiful about the rendering equation. So the
Okay.
also the path trace, that's actually very very powerful to make this one looks real.
Okay, and then one more thing, because of we know that they have an application on the calculus on that, which is maybe there lots of modeling that have calculus fundamental in there. So normally for this job, they have any software to solve, or you have to do it manually? I don't think that you have to do it manually nowadays, but
Um,
I just want to ask, because I have no ideas how you solve this thing, and then the result is quite interesting for me. So how you
well,
solve? Mhm.
yeah. So again, so um, there actually, so if you want to really want to test, the rendering itself, you can just run, you can just download the Blender and you just do any 3D object and render it, and you get the things done. If you want to do a very hardcore things, that's what I'm
Mm-hmm.
saying right now. So
Uh-huh.
you can write a program, you can write, a path trace program actually very, very, just like 200 lines or 300 lines usually. So that's enough to render all the things calculation. But I think
Mm-hmm.
this day, so you can just, by using any sort of the render, the research renders that we're using a lot in the graphics community. Actually, it's like, like Misupa, or sometimes they using, the NVIDIA's file code. That's actually one of the very proven things. You don't need to rewrite things, and you can add some of
Mm.
the research feature. Um, but again, you need to have some programming skill.
I see. Okay, so you need that skill, right? Okay.
Yes.
So any question from the audience? Any questions so far from the students, lecturers here? Now you can write if you don't want to unmute yourself. You can write the question in the chat box.
Yeah.
Actually, I can read it for you. There's no question.
Hi, Dr. Vincent.
Ah,
Hi.
Uh,
so we have question from Dr. Hakim. Okay.
so basically, this one is not my thing, lah. But I was just wondering if they say, because just now Dr. Vincent did put some comparison between three pictures with the different rendering. So basically, for Huawei itself, so which one is preferable? Which one is the objective?
So objective actually we want the pub trace.
Uh,
The pub trace is more because we want because the pub trace is like everyone want to solve everyone to achieve that kind of the result in real time. So yeah, so we that's actually we want to have this kind of quality because again, uh we don't want to go back to like 80s again. 80s, like the game console graphics quality.
Mhm.
Okay, okay. I think
Yeah.
Is there any application for the beginners if you want to try all of these technologies actually that you
So
can suggest?
if you want to try any technology, so I would say like there's a lot
Mm.
of so for those students have very savvy on the GitHub or something, so you
Mm.
can go to find a Google search, a PBRT. So the
TB.
PBRT actually is one of the the open source render. So there's a very very good documentation for you to learn to render or just compile that program and then just run the sample and then you start to deep dive inside the material or that thing because again this is just a pure introductory, but again if
Mm.
you want to know more this one actually it would be like a one full course
Yes.
for one semester or
I
two
get it. I
semester.
get it. Okay.
So I
Okay.
don't
All
want to
right.
go to
Maybe we can extend more talk with you maybe later, right? Okay. So before we end, we have a photo session. This is before we end. But is there any questions so far before we start with the photo session from the students? Anyone? My students? Where are you guys? Because my student is from electrical engineering student. So
okay.
it's yeah, you are doing electrical, right, in PhD, right?
Yes.
So any of you from electrical EE? No one. Tired
Did
already.
anyone take EMAC electromagnetic
So
theory?
electromagnetic. No one, huh?
Maxwell, did you guys came
Oh,
across with the
yeah, I
Maxwell?
have. This is my student. No, no, no. Yep. No, no, no. Okay.
Yeah.
Oh, yeah, my student. Okay, so here's a question from students. Let me read for you. How long
Yeah.
would it usually take to complete an image?
um
Hmm.
Okay, so if you are using, okay, so I can tell you some of the scenario first, okay? So if you're using some of the, offline render, macam iRay, V-Ray, those like, using for the product rendering. So that one actually would take like few minutes to render. But if you want like very high and crazy, that would take like hours to render just one image. And the time of the image rendering finish actually depends on the resolution. So biasakannya, we render the image in 8K or even more. So then
Mm-mm.
that would take forever to finish it.
I see. Okay. All right. So
Yeah.
thank you for that. Okay. I have more question here from the Amirah
As
Huda. So start. Okay. So what kind of a graphic card you usually use for rendering? Huh?
so we have different card in the office here. So we have like 3090, 4090, the 4080 or something like that. Also, we also try not just one GPU, two GPU, four GPU rendering.
Mm-hmm. Okay.
So it's very very interesting because then you see even you have more GPU, it doesn't mean like your speed will be X time faster, you know.
See. Okay.
So, but they have lots of very system wise issue, very very interesting. That's
Okay.
current hardware advancement. So,
Interesting right now. They
can, can you read the question, Mira?
okay,
I
yeah,
just can.
I can read it for you. Okay, so does current hardware advancement influence the efficiency of the AI accelerated path tracing techniques? Yep,
Yes.
you
Okay.
get the question right?
So okay. So I can share some of the what I see from the past of the hardware launch because again there's a team red, what the brand is, okay, and the team green. Okay. So the team green, so they start to launch, again, the GPU actually start to have a bottleneck, because on the GPU side here, so the hardware actually not just like one GPU for the graphics processing, unit, like the CUDA. CUDA that's actually specialized for the NVIDIA. And also AMD, they also have specialty. But the problem actually is that, whatever they launch, to do the calculation, so they reach to the bottleneck, for this kind of the normal graphics calculation. Now, so they start to increase the die size for the AI, so the specialized for the, for the for the AI accelerated part of this kind of calculation. So you can see that, actually they are not making this the graphics computational faster, more powerful, but then now they're making more the AI part become more powerful. So, but they're still inside the same GPU architecture. So again, I would say, like, the influence on this one, I would say future GPU, they are more and more rely on the what call like the AI to achieve these kind of effects. Yeah.
All right. Okay. So we have more. Okay, hiring. Okay. Okay, so the question here is, we know RAM have increased the price because of AI. Will it affect the graphic and the card price?
This is also not. It's very speculative to answer this. But again, there's some, the demand and supply issue, because I think that's always a problem. Again, it's hard to tell, because again, this is just like, some of the, the AI data centers, so they are relying on the, the memory chip. But obviously that will be, making the hardware become more costly in a short time. I think it's very, very hard to, to predict that. So I think it's very speculative. Yeah.
Okay. All right. Okay, so any other questions so far?
Come on, more. Yeah.
No more.
Bring more. Yeah. Bring more. Yeah. I know
Okay.
people shy in the like, student maybe shy in the beginning. So,
Yeah, at the beginning, yes. When
so
someone start asking, and then there are more questions so far. Okay,
yeah.
so yeah, we're still waiting for the question. Oh yeah, yes, we have more here. Okay, so I read it for you. So this might be out of the topic. Okay,
Yeah.
so here, can you share your path that make you achieve to work at Canada? This is because of the beasiswa that you choose, or intern place, or any other things. Yep, good one.
Yeah. Oh, okay. So, so other intention that over study overseas ni.
I know the story already.
Okay. So I would say, like, because again, to get the offer from the overseas university is not that simple, but again, you also not possible, but you also have to try to email the professor as much as possible. That actually will help you to get yourself enrolled. Again, know your professor, know your, what the field that you want to do it again, and then you craft the email based on, that professor. You don't craft the, generic email, then it's just, just spam it. So I can tell you, my most professor was receive like thousands of this kind of email. Can I be your, master students or PhD students or graduate students for this program? I'm very interested. I can. It would do that. So again, doing something like, tailored to that professor's specialty, and then you write it, and then so hopefully you just hook the professor that will reply. Actually, it's like, mine was within an hour, so he replied it, and then so we have a very good conversation, and then in 1 week time, so we got the offer, and then we just move again. So then we just study here, and then so my professor provide some of the, the what do you call it, the stipend. Stipend means like, like a GRA, for you to survive. But I would say, like, there's lots of costs you have to consider, that, like renting is not cheap, and also some of the living expenses also very things that you need to think about it. Also, you can work part-time, but again, it's just like you're trying to strike the balance between, your studies and also your your what I call like the mental health. Again, that's actually
Yeah,
mental health. Yes.
yeah, mental health
Yeah.
very important here.
Yes. Yeah.
Okay. All right.
It's possible.
It's
Yeah. And
possible
also
actually.
one
I
one
agree.
thing for sure, Yeah, one thing for sure, I think, when you're having the chance to do a research or cutting edge research, and also find, doing really, really hard for that, and then also go for the best, journal, best journal or best conference as much as possible, and actually that will reach you to distinguish between, other graduate students that you are, because that's actually the big tech companies are looking for you.
Oh,
You're not looking them; they're looking for you.
nice
Yes,
one. Yeah, very nice.
yes.
Okay. So, any further question from the student or the lecturers? Maybe baru terfikir nak tanya ke kan? Career apa? Change career path ke kan? Okay. 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 So if there's no more question, I think that's it. It's enough. It's really enough for us for this talk. Okay. So before we end, maybe can we have a photo session? Is that okay?
Yeah,
Okay. So
sure.
the student, please open your camera. Boleh? Buka. Jangan malu-malu. Let's have a session. Photo session.
Um,
Oh,
Mungkin you
sorry.
can give them 2 or 3 minutes for them to prepare for before
Oh,
opening up the camera.
camera. Oh, yeah.
Need 2 or
This is
3 minutes
lunchtime.
first.
Betul, betul.
Uh,
Lunchtime for us and then late dinner for Dr. Vincent, ya? Late
what
dinner.
time is
Okay.
it now okay, right now with the Vincent?
Vancouver. It's like 9:12 p.m.
9.
9:30 a.m.
9:12.
But you still
Yeah.
Tuesday, right, Vincent? Still
Yes,
Tuesday, kan?
Tuesday.
Ah.
Yes.
Oh, okay.
Kita
So
dah
I finished
Wednesday.
work.
Yeah, already Wednesday.
Yeah.
We
Yeah.
are from
So
future.
yes, you talk to the future. Yeah. So
Yes.
So that's why I finished work early today. So I went back home, just get some time to, to prepare, and then, yeah, excited to see you guys, to talk to you guys. Yeah. Good.
Okay, so okay, kita still wait for the student to get ready and take some picture. Okay, Isham still here, my student. Jeremy also still here. Okay, Farhan still here. Haris and Amir still here. Uthman also. Checking my student. They have they have a class with me previously. Yang lain ni belum lagi. Okay. Macam mana? Can we start the photo session, Puan Nur Zalila?
Maybe 1 more minute, sir, because we
One more
cannot see
minute.
the girls yet. Maybe
Yeah.
they are
Oh,
baru
the
nak pakai
girls.
dressing
Oh,
room.
betul. Okay, betul. So kita tengok
Right.
all the boys kan?
Semuanya
Yeah.
baru boys saja.
Tu dah student saya
Because
ramai.
girls maybe need some time to make up, kan?
Okay, kita give some chance Boleh Vincent? Okay, so
Okay, sure.
boleh buat small talk lah. Leisure
Yeah,
wine.
small talk.
Student, if you
Yeah.
want to talk with Dr. Vincent also can. Unmute
Yeah.
yourself. Boleh juga borak-borak. Sambil-sambil
Yeah.
kita tunggu kawan-kawan nak bersiap take picture.
Yes.
Ada?
Mira, macam mana nak scroll? How to scroll the rest of the student?
Oh, nak scroll lah.
Macam kalau pakai Meet ni tak boleh
Kalau
Itulah ada Dr. Hakim ni apa ni?
Dia limited rasanya.
Jadi
Tapi
first
sepatutnya
saja. Only the
sepatutnya
first.
120 ni selalu cukup untuk one screen.
mana tak nampak macam nak buat?
Tapi macam tak. Not
Hakim
every.
kan boleh buat ke satu screen?
Oh. Limited lah. Sekejap.
Kalau yang dulu boleh letak macam apa audience kat stage kan. Macam tu kayak ni tak.
Tu ada. Nampaknya limited lah. Yang the rest 80 tu tak boleh nampak.
Oh, ya ke? Oh,
I see.
ruginya. So far at the beginning is about 170 student I notice. Okay, because of dah ke late lunch kan.
Maybe some of the student ada kelas at 2.
Some of them, yeah, kena
Jadi I
get.
think kalau buka kamera then dia akan appears dululah.
Okay.
Ha.
So make sure tolong buka.
For those yang nak masuk dalam gambar then buka kamera lah.
Aduh. Okay. Rini, you take in charge in photo session
Yeah.
Okay. Kalau once you ready, you boleh lah bagi tahu kita ready je.
Okay, try Okay, try first time. Sekejap
Ya, macam mana?
Okay, sekejap Okay, 1, 2, smile. Okay, one more. 1, 2, smile. Okay, freestyle.
Okay. Good.
Okay, 1, 2, smile. Okay.
Okay. Dah kan ni dah?
Dah.
So okay.
Nak bagi QR attendance ke?
QR boleh? QR attendance
But
and
attendant auto generate.
Attendance auto generate. So nak QR attendance ke tak payah?
Tak payah.
payah kan?
Auto generate je.
Auto generate.
Okay, so again, Dr. Vincent, I really appreciate your time, and then I can see you're not really well, but you managed to give a top 1 hour straight to our students and also my clique here. So really appreciate that. All right, so maybe we were gonna plan some more programs, something like this lah, right?
Yeah.
So far, thank you so much. Thank you also for the students. Okay, so join us for today. I hope that the insight and also the knowledge that Dr. Vincent share with you is really valuable. All right. Okay, so and also for the organizing committee, Dr. Hakim, Nur
Dr.
Zalina.
Amirah.
Yes,
Sorry, Dr. Amirah.
Oh.
Sorry, sebab if generate attendance from this meet, tapi some of the student might share kan?
Oh, yeah.
Oh.
Faham? Okay, it's
Yeah,
okay.
agree.
We're gonna send the link and also boleh bagi
I
link
think we
dekat
need to share the
for every
link.
student juga. Boleh. Okay. Alright. Again, thank you untuk Puan
Alright,
Rozalina, Dr. Rini, Dr. Hakim. Okay, so because of kita berjaya for this program, the first one with Dr. Vincent. Okay, so we end our program for today. Have a good afternoon and good night for Dr. Vincent. Okay. Alright. Assalamualaikum warahmatullahi wabarakatuh.
Thank you,
And share some of the link.
Thank you. Right. Yeah.
Boleh share.
Bye.
Okay, bye. Thank you, Vincent.